Welcome to my YouTube channel. Our topic today is the number system and their properties. This is what we mean by the number systems. We have the set of natural numbers represented as n. We have the set of integers represented as z. We have the set of rational numbers, the set of irrational numbers, and the set of real numbers. Now, among all these sets, which one is bigger? We discovered that the smallest among the number system is the natural numbers, followed by the set of integers, followed by the set of rational numbers, and the set of real numbers. Now, the irrationals plus the rationals make up the real number system. Now, this Venn diagram is used as an illustration on how the number system is related. We have the set of natural numbers in the middle. Then the set of integers contain the set of natural numbers. The set of rational numbers contains both the set of integers and the set of natural numbers. The set of real numbers contains both the set of rational numbers and the irrationals. Let's look at some examples of the number system. The example I have here says you should prove that repeating decimals 0.11111 and so on is a rational number. To prove that, we denote our repeating decimals as x equal to 0.11111. Now multiply both the left hand side and the right hand side by 10. If you do that, you're going to get 10x equal to 1.11111. I call the first expression equation 1 and the second one equation 2. And when you subtract equation 1 from equation 2 component wise, you're going to get 9x equal to 1. Therefore, dividing both sides by 9, you're going to have that x is equal to 1 over 9. Hence, the repeating decimal 0.1111 is equivalent to the fraction 1 over 9. This is a major property of rational numbers. Rational numbers actually have recurring decimals and what is called repeating decimals, but irrationals don't have that, even though sometimes they look like fractions, but they are not fractions. This is one of the factors that is used to distinguish between rationals and irrationals. Now let's look at mathematical induction. The word induction means the process of reasoning from a particular case to a generalization. The principle of mathematical induction is used when proving statements that involve a positive integer n, and is stated as follows. Let Pn be a statement associated with each positive integer n, and suppose the following conditions are satisfied, which is that P1 is true. Number 2 condition is for any positive integer k, show that if pk is true, then pk plus 1 is true. Then Pn is true for all natural numbers n. Method of proof of mathematical inductions. In step 1, we prove that the statement Pn is true by substituting n to be equal to 1. In step 2, we assume it is true for n equal to k. And step 3, you now prove that it is true for n equal to k plus 1. Now, where one of these steps fail, then you say that the statement is incorrect. But if the 3 steps are satisfied, you conclude that by the principle of mathematical induction, the algorithm or the step or the recursive algorithm is correct. Let's take one example. You prove by principle of mathematical induction that 1 plus 3 plus 5 plus dot 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 is equal to n squared. How do you use the principle of mathematical induction to prove this statement? It's very simple. The first is you substitute, you identify your Pn, then you substitute n equal to 1. And when you do that, you see that the left hand side will be equal to the right hand side, which is a fact. Then you move to step 2, which says that assume that it is true for n equal to k. So anywhere I have n, I'm going to replace it with k. Having done that, then I move on to step 3. Anywhere I have n ab initio, I should replace it with k plus 1. So when you do that properly, you're going to have something that looks like this. Your pk plus 1 will not look like this. But it's important you identify your left hand side and your right hand side so that you have a clear picture of what you're doing. And when you simplify your left hand side properly, you're going to have k squared plus 2k plus 1 minus 1, which will give us k squared plus 2k plus 1. And at the end, when you observe from your left and right hand side now, you will see that k plus 1 squared will also give us k squared plus 2k plus 1. So the left hand side is actually equal to the right hand side. So you say if pk plus 1 is true, therefore by the principle of mathematical induction, Pn is true for all positive integers for n. So for this particular example, the recursive algorithm is true. Let's look at another example here. To prove by induction that 11 raised to power n minus 8 raised to power n is divisible by 3 for all n in n. Proof. For n equal to 1, when you substitute n with 1, you see that you get 3. And truly 3 is divisible by 3. Now you assume it holds for n, that is 11n minus 8n will be equal to 3t for some t that is in R. We want to prove it holds for n plus 1, that is anywhere I have n before, I should replace it with n plus 1. Then by the time I simplify, I will verify whether what I have will be divisible by 3. That is the trick behind principle of mathematical induction. Now 11n plus 1 minus 8 raised to power n plus 1 is equal to, I've been able to expand it, so I have 11 times 11 raised to power n minus 8 times 8 raised to power n. And when I add a special 0 in between, special 0 here is minus 11 times 8 raised to power n plus 11 times 8 raised to power n. They're actually 0, that's why we call it special 0, but we usually add it to help in the simplification. Okay, and when you do that simplification properly, you discover that you're going to get a factor 3. 3 in bracket 11k plus 8n. So because there's a 3 that is factored out, we say that 11 raised to power n minus 8 raised to power n is divisible by 3. Hence, by the principle of mathematical induction, we conclude that it holds for all n that is in n. I have another example here. It says we should prove that x y raised to power n is equal to x raised to power n, y raised to power n for all positive integers n. The same pattern, the same principle. You identify your Pn. In this case, our Pn is x y raised to power of n. Then you prove that when I substitute n to be 1, the left hand side will actually be equal to the right hand side, which is true. Then you move on to replace n with k. And when you do that, you're going to have pk equal to xy raised to the power k, which is equal to x raised to the power k, y raised to the power k. Now the next step is anywhere I have n, I should replace it with k plus 1. So you start with the left hand side, then you observe whether you are going to arrive or have the same thing with what is on the right hand side. That is how it's done. So we are starting with the left hand side, which is xy raised to the power k plus 1. And after doing the simplification, we got x raised to the power k plus 1, y raised to the power k plus 1, which is the same as what we have on the right hand side. So for that reason, say in conclusion, by principle of mathematical induction, P.N is true for all positive integers. Thank you for watching.